Okay, so today we shall discuss about simple harmonic motion. In this simple harmonic motion, what are the conditions? First of all, we shall discuss about what are the conditions here. So the first condition is it should be a to and fro motion. It should be to and fro motion. What do you mean by to and fro? This is to and this is fro. That is the meaning of to and fro here. Second one is it should have same path. What is the meaning of same path? Here this oscillation is following the same path. Okay, so in this oscillation, if you observe, it is following the same path. That is called as same path. Third one is acceleration is directed towards the mean position. See, acceleration is directed always towards the mean position, and here velocity is 0 at this place because the bob is going to stop here. Here at this place, which is called as mean position, where velocity will become maximum. Here at this extreme position where the bob is going to stop and return back here. So in these two cases, bob will stop and return back to the mean position. Therefore, velocity is maximum at the mean position. Velocity is going to be 0 at the extreme positions here. Next, acceleration is always directed towards the mean position here. Next, fourth condition is acceleration is directly proportional to displacement but opposite in direction. Okay, for example, you have considered the acceleration. Here velocity is 0, velocity is maximum, means acceleration is in this direction. Here velocity is 0, here velocity is maximum, means acceleration is in this direction here. But anyhow, acceleration will be towards the mean position, whereas displacement will be away from the mean position. Therefore, acceleration is directly proportional to displacement but opposite in direction. Okay, so therefore we can write acceleration is equal to minus k into x. Okay, so this is the here conditions. Next, fifth one is it is represented by harmonic functions. Simple harmonic motion is represented by harmonic functions like sine. Okay, sine function it can be represented. Okay, and this is having constant time period. The sixth condition is time period is going to be constant in this case. Okay, so in a simple harmonic motion, time period is going to be constant here. So these are some of the conditions for simple harmonic motion. Next, we shall discuss about time period of a simple harmonic motion. So how much time the how much time the pendulum will take to take one single oscillation, and from how the oscillation starts, let me discuss here how the oscillation is going to start here. For example, this is the pendulum. Let me start how the oscillation starts, and let me tell you how the oscillation starts here. So oscillation starts from the mean position. It goes to the extreme position. From extreme position, this goes to another extreme position, and from here again it comes to the mean position. And this is going to be completely one oscillation where it is called as time period. So mean to extreme, extreme to another extreme, and another extreme to the mean position again. So therefore this is called as time period, and therefore time period is going to be constant for each and every oscillation here. For example, in this oscillation, time period is 2 seconds. Okay, that means for second oscillation also time period is 2 seconds only. For third oscillation, this is third oscillation, time period is going to be 2 seconds only. For each and every oscillation, if time taken is constant, therefore we call time period is going to be constant in the case of simple harmonic motion. So these are some of the basic conditions which you need to understand in the case of a simple harmonic motion. Okay, next we shall discuss about what is the time period of a simple pendulum. How are we going to find out the time period of a simple pendulum? Here there is one force acting here. When the pendulum moves from, this is going to be the mean position, this is going to be the extreme position. When the pendulum reaches an extreme position, there is one force which will restore in the pendulum, which brings back it to from extreme position to mean position, and that force is called as restoring force. A restoring force is always opposite in direction. A restoring force will be in this direction, that is called as minus mg sin theta here. Because mg is acting downwards on the pendulum bob, tension is acting upwards, this is taken as mg cos theta. Therefore, I can write one step here. The step is going to be tension T is going to be mg cos theta. This upward force which is taken as tension and the downward force which is in the opposite direction, both are equal here. That is mg cos theta. Then restoring force means what? When the pendulum moves from mean to extreme position, one force will restore in the pendulum which tries to bring back the pendulum to the mean position from the extreme position. And that will be in the opposite direction to the direction of motion of the pendulum here. That's why that restoring force is considered to be negative always. So therefore, let me write the formula and try to derive and show you here. We can write now, the restoring force is going to be minus mg sin theta here. And you know, restoring force, any force we consider, according to Newton's second law, it can be taken as m into a, which is minus mg into sin theta here. Acceleration gets cancelled. So a can be taken as minus g into sin theta here. Now, if theta is very small, then what happens? If theta is very small, in trigonometry, we can consider sin theta is equal to theta here. Okay, so therefore acceleration is going to be minus g into theta. Acceleration is going to be minus g into theta here. But now, if you take this part of the pendulum as one sector and separately discuss about that here, then what are you going to get here? According to the concept of mensuration in geometry, we can take arc of a sector. This is going to be arc. Arc is equal to radius into angle. In this case, arc is considered as distance y here, and radius is nothing but the length of the pendulum here, and angle is theta here. Therefore, y is equal to L into theta. That means theta is equal to y by L. This theta value, if you substitute here, you know A is equal to minus g into, instead of theta, I can write y by L here. So therefore, acceleration can be considered as minus g by L into y here. Okay, separately I am considering. Let us imagine this to be equation number 1 here. So according to our previous knowledge, we know that acceleration is given by minus omega square into y, which was derived in the previous class. If you want, you can just check it. Acceleration is given by minus omega square into y. Next, after that, you will compare 1 and 2. If you compare 1 and 2, they are going to be same. Almost acceleration left hand is going to be same. So this is also same. Then what are you going to consider? Omega square is considered as g by L here. This implies that omega is equal to square root of g by L here. Under root of g by L here. But you know that omega is nothing but 2 pi by capital T here. 2 pi by capital T, which can be taken as root of g by L here. Okay. So if you take root of g by L, then what are you going to get here? Time period. Let me do the reciprocal to this. This will take a reciprocal here. You will write T by 2 pi is equal to root of L by g here. So this can be written as, this implies that this can be written like this. T is equal to 2 pi root of L by g here. T is equal to 2 pi root of L by g.